Okay, now I would like you to try some examples at home, and again if there are any doubts you can clarify with Mr. Tony. Okay, so let me ask you to check linearity. Check the following systems, following discrete time systems for linearity. For linearity. So, you would have to check additivity and scaling. Y of n is equal to n times x of n. 2. Y of n is equal to x squared time of n, squaring function. 3. Y of n equal to the real part of x of n, if x of n was a complex number. Okay. Number 4, y of n equal to x of n multiplied by x of n minus 1. Would like you to check for these things. Okay. Then we looked at another important property which said that if I delay my input or advance my input by some units of time, will the output also be correspondingly shifted? This is the property of shift invariance. Okay. Let me ask you to check for a particular example. Example, y of n is equal to sine of x of n. Okay. I hope you will agree with me that when you ask the question whether this is linear, the answer will definitely be no, because you are taking sine of something. That is not a linear operation at all. Okay. So, if you take alpha times x of n, it is not going to come out as alpha times sine of that. So, basically it is not a linear function, but however what we are asking is not linear, asking whether it is a time invariant. Okay. So, if I have a input x of n minus n naught, this system will produce for me an output y of n, y1 of n, which will be sine of my input, sine of x minus n naught. Okay. Take my original y of n and delay it by n units of time, y of n minus n naught. Where does n occur? It occurs as the argument of sine. Sine has an argument which is x, and that has got a sequence, has got an argument n. So, this will be equal to sine of x of this argument will come out to be n minus n naught. This is the same as y1 of n. So, this system is time invariant. You can call, some books call it time, some books call it shift, both of which are okay. N naught is an integer, so you can think of it just as a shift. It's easy to, I mean, if you're comfortable calling it time, it's fine. So, basically this is shift invariant. Okay. As always, you need to try out some exercises to check how well you have understood this concept. So, let me suggest to you the following exercises. Okay. The first one, y of n is equal to x of minus n. Okay. Now, this is a very interesting sequence. Basically, you are doing a mirror image. Okay. Now, if you shift in one direction the input, what will happen? The output will shift on the opposite side. So, it is not shifting on the same side. So, again very interesting to see that this will be obviously a system that will not satisfy shift invariance. Okay. Now, second, y of n is equal to a times x of n. We know that this is a linear system. Is it a shift invariant system? Number 3, y of n is equal to n times x of n. Okay. And the fourth one, y of n is equal to a downsampled version of x of n, x of 2n. Check these, verify, and then we will look at it and discuss it further. So, this brings up to the important category of functions or discrete time systems which satisfy both linearity and time invariance. We have looked at several examples which we now have. So, basically you know how to check for linearity, you know how to check for time invariance. So, now apply these concepts in the following manner. First step, okay, any x of n can be represented in terms of a summation minus infinity to infinity x of k delta of n minus k. Okay, this is nothing but the representation in terms of scaling and shifted unit impulses. I think this is from the first property. Second property, this input is being applied to a discrete time system t. So, we call it y of n is the output of this discrete time system t of x of n. T of x of n you substitute from equation 1. Okay, so, from equation 1 y of n is the transformation of this summation. Okay. Now, what does superposition tell you? If I have x1 plus x2, I can apply x1 first, get the output, that will be y1. I can apply x2 and I get the output, that is y2. So, it says that by property of a linear system which satisfies superposition, the sum of inputs, right, I have different, so you have in, several scaled delta functions, unit sample functions. It is the same as each is the sum of the output of each of these individual unit sample functions. So, you take the transformation inside. This is because it is a linear system which satisfies superposition. You get sum of k equal to minus infinity to infinity, the input of these each of these samples being applied to the discrete time system individually. Now, x of k is a constant scale factor. By property of the linear system which has the scaling function, you can take that outside the operation. Now, you are only operating, the linear system is operating on delta of n minus k. Now, if the response of the linear system linear time invariant system to a delta of n, okay, if the unit sample function, if you call that as h of n, what will be the response to delta of n minus k? It has to be h of n minus k. So, by using the properties of linearity and shift invariance, so basically this is using the property of shift invariance, we come up with a very powerful result which says the output of this linear time invariant system to any input x of n can be obtained as summation k equal to minus infinity to infinity x of k multiplied by h of n minus k. Okay, x of k like a scale factor, h of n minus k, think of this as h of k minus k plus n. Okay, what do? You first shift by n, which is some integer, and then you flip it. Okay, so basically this is a product of two sequences, one of which has been shifted and flipped. Which has been shifted and flipped? In this case, h has been shifted and flipped. So, let us see if we can capture this in the expression of the. So, how do you obtain the output y of n? To obtain the output y of n, first we have to get the impulse response. So, this is the unit sample response. Unit sample response. Okay, and h of n is equal to the this linear time invariant system operating on delta of n. This is the definition of the unit sample response. This is unit sample, and very easy. You know, instead of applying the entire sequence, you just apply one unit sample function. You will get the unit sample response. Once you get the unit sample response, then you take the sequence x of n, you have to time reverse h of n. You time reverse h of n, multiply the two, add them together, you get the value for y of n. You shift, do the same operation, you get. So, at each shift, for each shift, you will obtain one output point. This operation is what we call as convolution, discrete time convolution. It is denoted by the notation with an asterisk. X of n asterisk h of n means you are convolving these two sequences. You can, the operation that you have to do is keep one of them the same, flip the other and then multiply and then add. So, this is the operation of convolution. Now, since you have already done the course on signals and systems, there you would have represented a continuous time linear time invariant system by means of an impulse response h of t. And you would have computed the impulse response exactly in the same way as a convolution between the input and the impulse response. How do we do that? It is computed not via a summation, but by a by a convolution integral, which goes from minus infinity to infinity. X of tau, the signal is retained, the impulse response is flipped and shifted, so that you can then do the compute the integral. So, this is the discrete time counterpart of the continuous time convolution integral. Okay, I hope you are comfortable with that. We will now look at the like an example which will help us really to understand this in a very good way. So, let us look at an example of an LTI system, given that this particular system is linear and time invariant or linear and shift invariant, which means it has an impulse response which can be computed. The impulse response has been calculated as h of n, and it is given to us to be equal to a power n u of n, where a is a positive constant which is greater than 0, less than 1. Okay. So, what can you tell me about a of n? It is a exponential that is decaying, because alpha a is less than 1. So, when you take it to the power, and it starts at time n equal to 0. So, it will look something like this. The first sample has got a value equal to 1, a power 0 is equal to 1. The next sample is a, the one is a squared, a cubed, and so on. So, basically you will see that it is going. So, 1 a squared, a cubed, and so on. So, basically that is the decaying exponential. Okay, this is the impulse response. We are given that the input is equal to u of n. So, the output is y of n equal to x of n convolved with h of n. This is given by summation k equal to minus infinity to infinity x of k h of n minus k. Okay, and it is helpful if you want to do it as h of minus k plus n. Okay, you can think of it as plus 1. All right. So, u of n, you know what it is, unit sample starting at time n equal to 0, all these values are equal to 1. Okay. Now, first sample y of 0 is equal to, write down the expression, k equal to minus infinity to infinity x of k h of minus k. So, that means n is equal to 0. So, therefore, you are going to flip the impulse response h of n. Okay. So, I am just going to, I will not label them, but you know the decaying exponential. Now, it is flipped. Okay. What is the product of, and it is zeros here, because it is basically starts at its u of n. So, the first sample here, this is x of n, this is h of minus n, and this is what we have. The product of these two will be equal to 1. Okay, this the one sample here, one here. That's what we will have. Okay. Now, we start to shift the sequence. Okay. So, y of 1 will be equal to summation k equal to minus infinity to infinity x of k h of minus k plus 1, minus k plus 1. Okay. So, basically the flipped sequence is going in the other direction, but so that basically means that h of minus k plus 1 at k equal to 0 you will get, so basically this will be a sequence which starts here, okay, this is equal to 1, this is a squared, a cubed and so on. Now these two have to multiply. So y of 1 will be equal to, the first sample is 1, the second corresponding there is, it's a 1 here, so it's equal to 1. This sample is a, so you get 1 plus a. Shifted by one more unit of time, you will get y2 to be equal to 1 plus a squared. Shifted in the other direction, y of minus 1, then there will be no overlap between the two, that will be 0, y of minus 2 equal to 0. Okay. So you can write down the following, that the output of this convolution can be written as 1 plus a squared all the way to a power n minus 1 u of n. Okay, only for positive values, negative values no value. So this can be written geometric series 1, this is equal to 1, I think this goes all the way up to a, right, yeah. So this will be 1 minus a power n plus 1 divided by 1 minus a, geometric series, times u of n. You can verify, if you substitute n equal to 1, you will get 1 minus a squared divided by 1 minus a. So basically you will get 1 plus a as the answer. You can verify that. So yeah, this is y of n. So the important thing to note is that you have to flip one of the sequences and then you have to keep shifting them, and every time you do point by point multiplication and obtain the output. Let me just pause for a minute, make sure that you are comfortable. Let me just repeat what we have said. H of n is a decaying exponential starting at n equal to 0. U of n is a unit step function starting at n equal to 0. Now, to do the convolution, I am going to flip, in this case I have flipped the unit sample response. So unit sample response, h of minus n is sitting here. Now the product of these two, so that gives me y of 0 will be equal to 1. Then I have to shift by 1 unit of time. Then I see an overlap of 2 samples, the product of them and add them together, I get 1 plus a. Shift by 1 more unit of time, I see an overlap of 3 samples, so therefore I get 1 plus a squared. On the other hand, if I shift to the left, then I will see 0, another shift to the left 0. So basically the output comes out to be a causal output sequence. Basically its output is there only for n greater than or equal to 0, anything less than 0 the answer is 0. Again, I hope you are comfortable with this. What I would like you to do is the following. Okay, we wrote down the following expression, y of n is equal to x of n convolved with h of n. Okay, and you can write down the expression for the convolution and verify that in fact what this is equal to is summation k equal to minus infinity to infinity h of k, let me see, x of k h of n minus k. Okay. So basically if you substitute n minus k equal to L, so the limits of the summation will still go from minus infinity to infinity. So now it will be L going from minus infinity to infinity. H, this becomes h of L, x becomes k to the other side, it becomes n minus L. So basically, so what this says is the output originally we flipped the impulse response. You can flip the input sequence and get the keep the impulse response without changing. So basically what this says is y of n is equal to x of n convolved with h of n. This is also equal to h of n convolved with x of n. This is called the commutative property. It does not matter whether you convolve the first sequence with the second or the second sequence with the first, you will get the same answer, which is what is represented here. So what I would like you to do is flip the unit sample response, flip x of n and shift and keep h of n without flipping, okay, without flipping, and verify. Okay, so basically you will have this decaying exponential, the unit sample will flip around and then you do the flip. So you should get the same answer, y of n same as before, okay. You should get y of 0 equal to 1, y of 1 to be equal to 1 plus alpha, y of 1 plus a, I think, okay, 1 plus a. The next one, y of 2 will be equal to 1 plus a plus a squared, and so on. Okay, you can verify. And basically, what we did was previously we flipped the impulse response, unit sample response. Now this time you're flipping the input sequence, and this is just to verify that you get exactly the same result in both cases.